I didn't give you the volumetric flow rate. That's true. It is in the problem statement. It's 2 liters per second. Yeah, I think the actual problem statement gives you the volumetric flow rate, and the initial concentration. It doesn't give you the initial flow, but you know, given 2, you can always get the third. Yeah.
There's no diluent?
No.
So
This isn't that problem. This is.
So 2 liters is only 0.4 moles?
Oh, I don't know. These numbers could be totally made up. I wouldn't put too much stock into them. But as far as I know, there's no diluent. We're not given any information about a diluent. And these are actually from a book problem, so they might have used unrealistic numbers. They might actually be realistic, but I think you guys will actually have this on one of the homeworks that I'm assigning today. It's going to be the same problem. So you'll actually have to do, rather than just watch, you'll have to do it. All right, so we're not going to be going through how to set up the spreadsheet. We've done that. All I'm going to show you now is the completed spreadsheet, and we'll talk about how does temperature change along the bed of the reactor, how would we expect it to change, and that kind of stuff. Is that readable, or do we got to go all the way down?
All the way. All the way.
And bigger. How's that? Okay. All right, so you guys can see that I have the same little table that I wrote up on the board. The stoichiometric coefficients, theta, heat capacities, and our molar enthalpies that were all given. Sometimes it's worth doing it this way. Sometimes it's better to just keep them, you know, like they are down here. So yeah, here's the initial flow rate, volumetric flow rate. Here's the initial concentration. And like I said, the actual problem statement doesn't give you the initial flow rate in moles per second, but it's just, you know, the concentration times the volumetric flow rate. I don't actually think I used this because I already had it on there. The inlet temperature is 300. The inlet conversion, just for the sake of being paranoid, since we sometimes have those interstage cooling problems, so I set here the inlet conversion is 0. Delta CP, you can use this function called sum product, and it will do what it sounds like. It's going to do this times this, plus this times this, plus this times this, and you get 0. Delta H of reaction, I'm just doing sum product, but now with the molar enthalpies, you get 6,000, just like we said. I think it's sometimes useful to have this little thing called inlet heat capacity, which on the board, it's just written as the sum of theta times the specific heats. Anyways, it's 30, so that's essentially for this problem, it's just CPA plus CPV. Again, you can use some product to do that. Activation energy is just given, 10,000. This K is given at a specific temperature, so I use that to calculate A. And you get 1.93 e to the 5, and then R. And then we have this delta V, which I only separate from the rest because it's not specific to the problem. It's just how did I set up my spreadsheet, right? It's about how I'm numerically solving these things. It actually has nothing to do with the problem itself. So before we look at some plots and some outcomes, what do we expect the volume for this reaction to be? For a CSTR, it was 175 liters. What do we expect for this problem? More? Less? More? So for PFR, the volume is going to be larger than for a CSTR?
Less.
Less. Okay, we'll see. The temperature, it's an exothermic reaction, right? So we expect the temperature to increase along the bed of the reactor. That's what we see. You just look at the first few points. What do we expect to happen to the rate of the reaction along the bed of the reactor? Why is it going to increase? The temperature is going up. Somebody said decrease. Why is it going to decrease? Because the concentrations are going down. Which one wins?
Probably going to be,
So it's actually going to undergo, it's going to go through a maximum point and then decrease. It goes up and then down. So if I take 1 over that, I know it'll be hard to read because we're in the dark here. But 1 over that profile so if the rate goes up and then decreases, then 1 over the rate is going to come down and then increase. Right? So again, this is our Levenspiel plot, and you guys might remember from way back in chapter 2 that a lot of Levenspiel plots look like that. They look like big U's. And it might have been like, why the hell is it going to look like a U? This is why. Okay, so let's first look at the temperature profile and conversion profiles. What do you notice? They have the same shape, right? I can superimpose these two. Does that make sense to you? Which is, do I need to label them? Look at the axes, man. One's 0 to 1, the other one's 300 to 500. The x-axis is length of the reactor, or volume, excuse me, volume in liters. So why do they have the exact same shape?
Corresponds to each other.
Yeah, but why? Because it's adiabatic. So the only thing that can change the temperature in this system is conversion. As I go to higher and higher conversions, I'm releasing, in this case, more heat from the reaction. The heat's giving off more reaction. And so the conversion and the temperature profiles match each other perfectly. And we've seen this before, right? We just saw it in a different way. What did our plot look like when we plotted conversion from the energy balance versus temperature? What kind of line did we get? Straight line. That's why. Because those two things have a 1-to-1 correspondence. Otherwise, I wouldn't get a straight line, and these two things wouldn't overlap. What was the special thing that had to be true, though, for this to give us a perfectly linear relationship? Yeah, delta Cp has to be 0. In other words, the heat of the reaction doesn't depend on the temperature of the reaction. And so that's why these two things are perfectly superimposed. If that weren't true, you would see differences, but they would be usually subtle. Because usually the change, the delta Cp, is not very large compared to the delta H of reaction. But delta H's of reaction are not always constant with temperature, right? It's just an assumption we keep making, probably to the detriment of your long-term knowledge. You're going to forget about it one day. Okay, so we can also take a look at the rate. So it starts to increase in the beginning. Why? Because the temperature is increasing, which has an exponential impact on the rate constant. Makes a big impact, right? It shoots up, but at the same time, when we know that at the end it has to be 0, has to be 0. If we've reached some constant conversion, no more reactions happening. So if you've gone to either the equilibrium conversion or a conversion of 1 in the case of an irreversible reaction, you know the rate is 0. So we know it has to come back down, and so that's what it does. And so we go through this maximum, and it's at a temperature of, or a volume, excuse me, of about 280 liters. Of course, we can also plot that. If we wanted to, we could have made a plot of the rate versus the temperature. again, we see a maximum, or you can plot it as a function of the conversion.
So just to confirm, the temperature increase at the beginning is due to, or I'm sorry, the rate of reaction increase at the beginning of the reaction is due to the temperature increase.
Yes.
And as the reactants are consumed, the concentration decreases, thus decreasing the reaction rate.
Yes.
Okay.
Or you've approached equilibrium, which means that the rate of the forward reaction is equal to the rate of the reverse reaction, so the net rate of reaction is also 0.
Okay.
This is an irreversible problem, so you can think of it as the concentrations of A and B are essentially 0. But that's not always going to be the case, right? If it's a reversible reaction, the concentrations you still might have a lot of A and B around.
Right.
But because you have a lot of C around, or you have enough C that it's just reacting backwards at just as fast of a rate. Okay, so if we were to imagine that we could operate this reactor yeah, so again, this is the linear relationship that I think I have it backwards versus what's on the board, but that's okay. This is the conversion versus the temperature. Again, it's linear, like we've said, and this is because delta Cp, or excuse me, delta H of reaction is not changing. Delta H of reaction is related to, but not equal to, the slope of that reaction. I mean, of that line. Okay, so if I make a Levenspiel plot, so my x-axis should be what on a Levenspiel? And my y-axis should be 1 over the rate, or you can have the flow rate divided by the rate, either one. This is what we get, and it's hard to look at, so I'm actually going to cut off the top.